here we're going to check out from example 2, we're going to use the remainder theorem to verify the remainder. So in the last example, we divided 2x plus 1 out of our polynomial, or our p at x, of 4x3 plus 9x minus 12. Okay, now I have to look at this and think, all right, well, does this look like an x minus b situation, or does it look like an ax minus b situation? Well, because there is a number in front of the x, I need to look at this one because there's a number in front of the x. And according to the remainder theorem, if I'm dealing with the ax minus b situation, okay, that means if I take that a value and that b value and I plug it in for x, so if I take my polynomial and I sub in the b, actually here, why don't I do it in other colors? If I take my polynomial and instead of x, I sub in b over a, if I sub b over a in for all of these x's, it will equal my remainder. So if that means when I sub in b over a into here, I should get negative 17. Well, let's take a look. So that means 2 is my a, and because it's a minus b, okay, let's actually take a closer look at this. So I'll bring it down here. 2x plus 1, all right? For a traditional ax minus b, we need a minus in there. So I can actually rewrite this as 2x minus 1, okay? Because a negative times a negative is a positive. So it's a lot easier to figure out what my a value is and what my b value is. So my a is going to equal 2, and my b is actually going to be negative 1, because I need to have that negative in there. So that means my b over a is going to equal, my b is negative 1, over my a value, which is 2. So this is what I'm going to sub in for my x value. So let's do it. So when I take my polynomial and I sub in negative 1 over 2, what do I get? So I've got 4 and negative 1 over 2 to the 3 plus 9 negative 1 over 2 minus 12. Okay, so negative 1 over 2 to the power of 3. So negative to an odd exponent is still going to be negative, but that 3, remember, that exponent gets distributed to both. So 1 to the power of 3 is still 1, but 2 to the power of 3 is 8. Okay, now this, remember, don't forget this, there is an invisible 1 under here, and if we're multiplying fractions, we just multiply the tops, multiply the bottoms. So this is going to become negative 9 over 2. That minus 12 just comes along for the ride. And now let's multiply this out as well. Multiply the tops, multiply the bottoms. So now we're looking at 4 over 8 minus 9 over 2 minus 12. And as I always remind you guys, reduce, clean up, and simplify as we go, okay? Because 4 over 8, we can reduce, can't we? Well, that is just the same. Oh, don't forget that negative. That is the same as 1 over 2. And now, both my fractions have the same denominator. So I can subtract those a lot easier. So minus 1 over 2 minus 9 over 2, keep the base, and in our case, subtracting the exponents. This will become, so minus 1, take away another 9. minus 10 over 2 minus 12. And I know that, right? Negative 10 divided by 2. Almost running out of space here. Negative 10 divided by 2, well, that's just negative 5. And negative 5 divided by negative 12, look at that. The remainder that I got back here at example 2. Okay, I got a remainder of negative 17. Okay, so I've now used, instead of doing all of this long division, I've found the exact same remainder, but using the remainder theorem.